Hello, and welcome to the Precision Medicine Pulse, your weekly precision medicine update. Fix my earphone again. If you if you'll notice, I'm in a slightly different setup today. So I'm not at my home base in Phoenix. I'm in Seattle to meet some clients this week and meet some friends too. I used to live in Seattle for 3.5 years, so I've got a nice little network up here. But that means this podcast is probably going to go out a little bit later today than what we usually do on Tuesdays. Today is Tuesday, March 11th. And but we'll still get it out. We've got an interesting show today. Quite a fun show. It's another week that's been lighter on the news, so we're going to go into a little bit more detail on CRISPR, and specifically we're going to focus today on delivery mechanisms for CRISPR. And the general theme that I've noticed over the last few weeks is last week we had a really interesting show where we talked about Yoltech's lipid nanoparticle delivery system. The week before, or maybe 2 weeks before, we were talking about Regeneron and how they had a delivery mechanism for treating a form of deafness caused by misfunctioning autoforlin gene. And that was a viral delivery mechanism for this gene editing, for that particular gene editing that Regeneron was doing. And so both of those delivery mechanisms, they work when you want to do the gene editing in vivo, or you want to do it within the body itself. This week, I came across quite an interesting paper in Nature Protocols. Let me share my screen. Give me 1 second. Do. Sorry for that there now. I should be sharing it right now, but it was this PERC related gene editing delivery mechanism. And the paper itself, this paper itself was published in Nature Protocols last Monday. I don't have access to Nature Protocols, but I was able to find the paper itself on the archive. And I had a quick read through it. And I think after reading through this, I think I've got my clickbaity title for the podcast this week, which is the end of electroporation. So electroporation is the predominant form of CRISPR delivery for ex vivo, or for when you want to do some gene editing outside of the body, so not directly in the body. We have two ways of delivering CRISPR. We can do it in the body or out of the body. Lipid nanoparticles, like the pH1 treatments that we talked about last week, they're really good for doing CRISPR related gene editing based in the liver. So because the liver is a really good environment for processing lipid nanoparticles, we can do gene editing in the liver quite well if we use that lipid nanoparticle based delivery mechanism. And there were some interesting people out there working on slight variations of lipid nanoparticles that could be accessed in more than in optimized for different organs. But that's generally, if you want to use that delivery mechanism, you're going to be looking at the liver as the organ. So you want to target something in the liver. Um, the viral type of delivery mechanism that has a broader scope. But if you're delivering your gene editing via a virus, there are like a little bit larger risks for a bad autoimmune response. So for a lot of cell therapies where you want to do some gene editing, a lot of it happens ex vivo or outside of the body. And the typical mechanism for doing it outside of the body is it's called electroporation, where you use a physical piece of hardware to, I mean, for lack of a better term, smash. Well, smash isn't the right word, but you want to use mechanics to force the CRISPR enzyme into the cell to inside past the cell membrane into the actual cell itself to do the gene editing. And there's a whole ecosystem of companies that have been built to, service this type of a need. And this PERC, this new mechanism, this new protocol that's designed in this paper, which is peptide enabled ribonucleoprotein delivery for CRISPR engineering. So this is like a quite a mouthful, but the overall mechanism that's on display here is an alternative or a potential alternative to electroporation. You know, it's quite early. We This needs to obviously go through clinical trials, but the way that they deliver the gene editing in this case with this approach is they attach a peptide to the CRISPR enzyme, and then that peptide is able to go through the cell membrane in a much more gentle, I think is the phrasing they used, in a much more gentle approach. So there's less kinetic force being applied here, which means less damage to the cells, which means it's a you're losing you have a higher yield in terms of treatment potentially than the alternative electroporation approach, which it's like, that could be, at least as they're proposing here, you can have an efficiency of over 90%, which is quite good for ex vivo genome editing. So early days for this type of treatment here, but if this does come to pass and this breakthrough does make it all the way through clinical trials, this is quite an exciting development for ex vivo gene therapy. Ex vivo gene therapy is like used quite frequently when you want to treat some type of an immune disease or some type of a blood disease. Like a lot of leukemias will be treated with this type of a way. You wouldn't use lipid nanoparticles. You would use electroporation typically to deliver, if it's a gene-based treatment to, a leukemia type of disease. And so I guess in essence, this new news story that I came across this week could potentially mean it could be the beginning of the end for electroporation. Now, that's a little bit of a clickbaity title. This is still lab stage, needs clinical trials. Even if it passes the clinical trials, it would need to be cost effective. It would need to be scalable. So I place this in the ballpark of other similar types of delivery mechanisms that are in development for CRISPR related delivery mechanisms. It's in the lab stage, but there could be some really exciting things around the corner. I was thinking to myself then, who would be the winners and the losers in the long term should this delivery mechanism make a break, come to pass? And you would think about cell therapy companies like Vertex or CRISPR or Beam, like those types of companies should do quite well if the way that they can deliver CRISPR-like treatments becomes easier, if the barrier towards delivery comes down. On the other side, potential losers could be hardware companies that make specific electroporation systems. So think about like MaxCyte or Lonza. But again, we're a little bit away from this type of breakthrough in the lab becoming a breakthrough in the industry. Yeah, that was the interesting article that I came across during the week. But yeah, I guess it's been again a slower week this week by all accounts. Evo 2, we're still coasting off of the back of that gigantic news, I think, a couple of weeks ago now. But it's interesting to get an opportunity to dive into these gene editing delivery mechanisms in a little bit more detail. Stay tuned, get subscribed if you're not already subscribed, and we'll be back next week with some more precision medicine updates. I've been your host, Gary O'Keefe. Have a great week. Ciao, ciao.